Okay, so having finished this section, we now start solving the exercises. The first one asks us to prove lemma 422, which we have already proved actually. So, as a solution, we just simply write we have already proved it. Then the second one, it has two parts. Part A is this: if f is the field of real numbers, prove that three vectors are given (0, 1, -1, 0 and 0, 0, 0, 3. In this space, the space of four tuples of elements in this field, where this of course for us now is the field of real numbers. These are linearly independent over F. So that is part A, and there is part B also. What conditions on the characteristic of F would make the three vectors in A linearly dependent? Conditions. On the characteristic of F would make the three vectors in A linearly dependent. So let us first show that over the field of real numbers, these three vectors are linearly independent. So that means the only linear combination of these three vectors with real number coefficients that is going to give us the zero vector is the trivial linear combination, where all the scalars or all the coefficients are zero. So to show that, we assume three real numbers such that alpha times 1, 1, 0, 0 plus beta times this second one 0, 1, -1, 0 plus gamma times the third one is equal to the zero element or the zero vector in this vector space. Okay, so now we want to find out this alpha, beta and gamma. This implies if you really calculate this sum on the left hand side, you get alpha, because you see here in this vector the first component is non-zero. In the other two vectors the first components are both 0. So we get alpha and that should be equal to 0. Then we look at the second component. We will have alpha here and beta here. Here the second component is 0. So alpha plus beta is 0. Then we look at the third component. The third components of the first and third vector are 0. Only in the second vector we have the third component non-zero, which is -1. So from this one we get minus beta equal to 0. And finally the fourth component of only the third vector is non-zero. It is 3. So we get 3 gamma equal to 0. From these we have alpha equal to beta equal to gamma equal to 0, because you see from the first, third and fourth equation you get them to be 0, and these 0 values satisfy the second equation also. So we in fact have shown that the coefficients must all be 0, and this proves that the given 3 vectors are linearly independent over F, the field of real numbers. Equal to gamma equal to 0. Hence the given 3 vectors are linearly independent over F. Next, in part B, we want to find some condition on the characteristic of the field F such that these same 3 vectors would become linearly dependent. And in this context you have to understand that now F is not the field of real numbers, because we have already seen that over it these 3 vectors are linearly independent. We have now proved it just now. But now F is any field. So you can see that if the characteristic of F is 3, for example, then this third vector would become the 0 vector, because if F is a field of characteristic 3, then in that field 1 plus 1 plus 1 is 0, and that's just the definition of 3. So this would become 0, and hence the third vector would be 0. But if you have the 0 vector in a vector space in some set, if the 0 vector of some vector space is an element in a set of vectors, then that set is linearly dependent. We have already seen these things. So we write accordingly. If F is a field of characteristic 3, then So in this case, the three vectors from part A are linearly dependent, and that is the solution. Next, the third one. If V has a basis of n elements, has a basis of n elements. If you are able to hear some sound in the background, that is the cloud rumbling. Okay, I think it will rain very soon. Okay, so where was I? Okay, has n elements. Give a detailed proof that V is isomorphic to Fn. V is isomorphic to this space. We mentioned this fact in the text. I can't remember whether while discussing the things in this section, I really rigorously proved it or not. I can't remember. So because I cannot remember, so let me just do it. Okay, if we have already gone through that, then this will be a repetition, but sometimes it's okay to repeat things. Maybe you will come across some aspect of this proof which you may not have noticed before. So it is given that V is a finite dimensional vector space and its dimension is n, that is, it has a basis with n elements. So let us take such a basis. Let Vn be a basis of V. We define a mapping T from V into Fn as follows. Let small v be any element in capital V. Then, because capital S is the basis of capital V, So capital S spans capital V. That means this small v is a linear combination of these basis vectors because of that spanning nature. Then there exist unique scalars belonging to F, where of course it's assumed that F is the underlying field. Oh, F is already given, okay, fine. So there exist unique scalars such that V is this linear combination. Okay, now because S spans V, there exists such a linear combination of the basis vectors which is equal to V. Okay, that existence part comes from the spanning nature of S, and the fact that these scalars are actually unique, you will not get two different sets of scalars which will give you that same vector. The scalars are going to be whatever scalars you find which help you write V in this form, they are going to be unique, and that uniqueness part comes from the fact that S is linearly independent. The existence part comes from the spanning nature of S, and the uniqueness part of the scalars comes from the fact that S is linearly independent. Okay. Be defined the image of V under T to be equal to, whenever you define something, you use colon like this, colon to the side of that thing which is being defined, and the other side of this equality sign which does not have colon is the meaning of this thing that is being defined. So you see that for a given vector V in V, we have got an ordered n tuple of scalars in F. That means this is an element in Fn, and this we will get for any vector V. One more thing is that these scalars, because they are uniquely determined by V, for a given V there exist unique scalars, so this image is unique, and that is why the function T is, mapping T is well defined. Uniqueness of the scalars for a given vector V shows or implies T is well defined. Okay. Let us take another vector, say W belonging to V. For this W also, we will similarly get some unique scalars, a set of unique scalars. Such that W is also one such linear combination of these same basis vectors. The basis vectors don't change, the scalars change, and they give us different vectors in the vector space V. Okay. The purpose for considering another vector W is, of course, you can imagine, we are now going to show that T is a homomorphism, vector space homomorphism. Now, okay, so first of all we try to show that T preserves addition. So we apply T on this sum, V plus W. On this we are going to apply T. So looking at V and W and using the several properties that the vector space V has, its axioms, we can write V plus W like this: alpha 1 plus beta 1 V1 plus alpha 2 plus beta 2. Let me not just write alpha 2 plus beta 2. It is there, you can understand. Because of lack of space, I am not writing it. So immediately I use ellipsis and then alpha n plus beta n Vn, and on this we are applying the function T. Okay. Now you can see that this again is a linear combination of the basis vectors, and whenever we have such a linear combination and then we apply T on that vector, on that linear combination, the result is this. And we don't in fact have to think about what these scalars are. Linear independence of S makes sure that you can in fact so what I am trying to say here is that this linear combination that gives us V plus W is the only linear combination of these Vi's that gives us V plus W, because of linear independence of S, and that comes from the uniqueness of these scalars. So if you have found one linear combination, that is the only one. Okay. Now by the definition of our function T, this is alpha 1 plus beta 1, alpha 2 plus beta 2, those things are there, alpha n plus beta n. Now in the space Fn, this thing equals the sum of these two intervals. This is the vector addition we have in Fn. Now this again by the definition of our function T. If you look at what these vectors are, v and w. We don't have v here, but we can see w here. So this is nothing but the t image of v, and this one is nothing but the t image of w. So t indeed preserves addition, vector addition, and for any scalar alpha belonging to F, we have, so next what we do, we apply T on alpha phi. So which is what? Alpha 1 v1 plus alpha 2 v2, like that up to alpha n vn. Again, using the several vector space axioms, we can write this entire thing like this. If you are not really comfortable with applying these vector space axioms, then I suggest you go step by step. For example, what we will have to do in order to get this from this. Okay, forget about t for a moment. You know that if alpha is a scalar and you have said two vectors v1 and v2, then one of the axioms tells us that this is equal to alpha v1 plus alpha v2. That's what we have applied here first of all, but not just this, its extended version, which does not necessarily have only two vectors. It can have any number of vectors, n, where n can be anything, n can even be 1 also. Then you get this, and then in each such term you will have this. Now, for example, here, after performing that first thing, you get this. But this again, another axiom tells us that this is equal to alpha alpha 1 v1. So that's how we ultimately get this thing. Again, now we are faced with a linear combination of the basis vectors on which we are applying t, so we can directly use the definition of t, and this will be equal to this n tuple alpha alpha 1 alpha. Let's just write one more, n. But now in the space Fn, the definition of multiplication by a scalar is just this. By that definition, this is equal to alpha alpha 1 alpha 2 alpha n, and this is nothing but phi t. So t not only preserves or respects addition, it also preserves scalar multiplication or multiplication by a scalar, and that is why t is a vector space homomorphism, which also sometimes, in fact more frequently, we call such things linear transformations. So we now have a well-defined linear transformation or homomorphism from V into Fn. Hence, is a homomorphism. Because we are primarily dealing with vector spaces here, so there is no need to additionally write vector space homomorphism. But if you are in a general algebraic situation where there are many different kinds of things, say you have vector spaces also, you have groups also, there you have to mention separately what type of homomorphism you have. Okay. Next, now we try to show that this T is onto. So for that we will choose a vector here and we will show that that vector is the T image of something from here. Gamma n belong to Fn. It is some n tuple of field elements. Then obviously this is very easy actually. You consider this vector. Gamma n V, and this is obviously a linear combination of the basis vectors in capital V. So this is after all a vector in V, and its T image by definition is just this, such that gamma 1 V1 plus gamma 2 V2 etc. gamma n Vn T is equal to this n tuple with which we started. Hence T is onto. Next we show that T is 1 to 1. For that you can either directly show that as a function T is 1 to 1, or you can take the help of that small criterion that we have for 1 to 1ness of a homomorphism, namely that the kernel of the homomorphism consists only of the 0 vector in the domain. So let's just do that. Next, let us take something else. Let X belonging to V be a vector in the kernel of T. Now, being a vector in V, X will have its own expression as a linear combination of basis vectors. So, this is one such expression. There will be exactly one, but this is the one. Delta 1 V1 plus delta 2 V2 etc. delta n Vn, where these deltas are scalars. Okay, now because X belongs to the kernel of T, so the image of X under T will be the 0 vector, but where? Here. That means the 0 n tuple. Then you should understand that we have n components here. This is equal to xt because x belongs to the kernel, but by the definition of t, this is also equal to this, which implies by the definition of equality in Fn, the corresponding components must be equal. Hence, delta I is equal to 0 for all I between 1 and n inclusive. Thus, now x becomes 0 because all the deltas are 0, so automatically x is 0. This shows that the kernel of T is the 0 subspace of V. Hence, T is 1 to 1. So we have proved that T is a homomorphism, T is onto and T is 1 to 1, and that is why T gives you an isomorphism of V onto Fn, and thereby we have shown explicitly that V and Fn are isomorphic as vector spaces. Next, if T is an isomorphism of V onto W, okay, T is an isomorphism of V onto W. Since an isomorphism is given from V onto W, so that means V and W must have the same field of scalars, because otherwise this would not make sense. Prove that T maps a basis of V onto a basis of W. Now here there is a subtle thing which again Herstein has not bothered to make explicit, but we have to consider it, otherwise it will be a mistake. The thing is that the vector spaces V and W here we are considering can be the zero vector space also, namely that vector space which has exactly one vector. And as we have already seen, that particular vector space which has only one vector, the zero vector, has the empty set as its basis. So according to what is being asked here in this exercise, if that is the case, if our V and W are both the zero space, then both of them have this basis. And it is given that T is an isomorphism from V onto W. In this particular case, our T will be one fixed T, which will be this T, which maps the only element in this vector space to the only element in this vector space. And this map is trivially a homomorphism. In fact, it's an isomorphism of zero space onto zero space. Okay, so the hypotheses that we have here are actually true in this particular somewhat trivial case. However, then what the exercise claims is that T maps a basis of V onto a basis of W. Namely, T maps the empty set onto the empty set. Now here there is a problem. The problem is that the notion of function or mapping that we have in this text in Herstein's topics in algebra does not cover this single case. If you go back to section 1-2 where we have defined functions or mappings, you will see that we have defined a function f from S to T where both S and T are non-empty sets, but there in fact is a notion of an empty function, and if you take into consideration that notion, then there is actually no problem with this. In fact, what I am saying is that although it may seem like there is a mistake in the claim of this exercise in this particular case, but actually that is not a mistake. It looks like a mistake because we don't have the notion of empty function in this text. If you want to introduce empty functions, then everything is okay, but let's just not define the notion of empty functions. Let us just not complicate matters just for this one trivial case. But then, and that's what I was saying when I said that Herstein messed up a little bit, he should have mentioned that these are non-zero vector spaces. Okay, and that's what we are now going to do. We are going to make that additional assumption that V and W are non-zero, because we don't have this thing with us in this text. The notion of empty function is just one convenience. It is logically there is no problem with this notion. It's somewhat like the notion of the empty set itself. You can do without it, but if you have it in your theory, then many things become easy. Correspondingly, it's just like the notion of the number 0. Okay, there is no logical fallacy or mistake with these notions, but they don't necessarily correspond to things outside of mathematics. So what I'm trying to say here is that, for example, we have been taught in when we first encountered mathematics in school, we were taught about the numbers by associating these entities with some sets: 1 banana, 2 apples, 3 pens, 4 tables. So when we look at the number 0, we don't see any such association and we get confused. But that confusion is only superficial. I mean, because of the way we are taught about numbers, we tend to think that anything we are taught, anything mathematical, it has to have some real world connection. That is not necessarily true. A mathematical system is a logical system which starts from some axioms and then it progresses logically, taking those axioms as true or self-evident. We then prove more and more complicated and interesting things. If at all your system finds an application, fine. Otherwise, there is nothing, no problem with the theory itself. It's like, what can I say? It's like sewing a shirt, say. Okay, you can make a shirt or something that resembles a shirt in any way you want. You can make different sorts of designs. So that is mathematics. But when you apply that thing, when someone tries to wear it, then you have to see which shirt fits that person the best. If something does not fit anyone, that is not that thing's fault. Okay, it's not, its primary aim is not for application. It is being made for its own sake, just for the sake of interest. Application is bonus. Okay, so that's why we sometimes see things like empty set, zero, empty function, which seem like unnecessary, but no. Everything cannot be judged in terms of how applicable it is. We do mathematics primarily because it is interesting. Application comes afterwards. If it doesn't come, that is fine. B assume that both P and W are different from the zero space so that the bases of V and W, whatever bases we have, none of them will be empty. Okay, they will have something. Let S be a basis of phi. Note one more thing, that there is no condition on the finite dimensionality or lack thereof of these spaces. They may not be finite dimensional, okay, but S is some basis of V. So B are being asked to show that T maps the basis of V onto a basis of W. So that means we have to show that the image of S under T is a basis of W. We now show that the image of S under T, ST, is a basis of W. I reiterate, because V is not necessarily finite dimensional, this S may not be a finite set. Okay. Am I saying it correctly? Yes, no condition about dimensionality is given. Okay, fine. Now, in order to show that ST is a basis of W, we already have one thing, that ST is a subset of W. That thing we have. Now, we need to show that ST is linearly independent and it spans W. So, let us show the span thing first. Let W be any element in W. Okay. Since, so the original T, the function is an isomorphism of V onto W. So it is onto. So since T is onto, there exists some V belonging to the domain such that W is equal to the T image of V. Now, because V belongs to V and S is the basis of capital V, so that means this vector will be some linear combination of some elements of S. Now, there exist vectors S1, S2, etc. How many we don't know, but some finite number of vectors. And one more thing, I am writing vectors, scalars. There is no actual need to use these words. You can just simply write elements. I am doing so in order to distinguish between vectors and scalars. You can of course distinguish between them just by looking at the equations or whatever, wherever they come, wherever they appear. But just to make things much more clear, I am additionally saying which things are vectors and which are scalars. So because V belongs to V, so there are some vectors such that V is some linear combination of these vectors. So we are in another exercise now, so I can again use alpha. Alpha n Sn. Where the alphas are of course scalars or field elements. Hence, so now with this new information, what do we have? W is Vt, which is this thing, and that is equal to, okay, now use the fact that T is a homomorphism. So it will preserve addition, scalar multiplication, both the things. So we can write this entire thing like this. Vnt. Oh, what the hell? These are S. It's become a habit to write V's. So you can see that these are vectors, these SITs are vectors in ST, and we have been able to show that V is a linear combination of these vectors. Which shows that V is a linear combination of some vectors in ST. But V was no, that is not what I wanted to write. W is a linear combination, but W is an arbitrary vector in capital W, hence ST spans capital W. Next, we want to show that ST is linearly independent. So that means if we choose any finitely many vectors from ST and an equal number of scalars from the underlying field and form the corresponding linear combination, that linear combination will be 0 if and only if all the scalars are 0. Next, let sigma 1, sigma 2, etc., say sigma m belong to S. We have chosen these vectors from S because we want to look at their T images, that is sigma 1t, sigma 2t, like that up to sigma mt. We want to show that these are linearly independent, because then ST will be linearly independent. So let beta 1, beta 2 to beta m be scalars such that this linear combination is 0. Sigma 1t beta m sigma mt is equal to 0. Okay, now where can we go from this? Again, use the fact that T is a homomorphism to take everything inside. You know what I mean by that. This implies I need ink. This implies what? Okay, because T is a homomorphism, the image of the 0 vector under T is again the 0 vector. This is the 0 vector in V and this is the 0 vector in W, and that 0 in W is equal to this beta 1 sigma 1 T etc. plus beta m sigma mt. Now, using the fact that T is a homomorphism, this can be written as beta 1 sigma 1 etc. beta m sigma m T. So, the T images of 0 as well as this vector are both equal to 0. So, outputs are equal and T is 1 to 1 because T is an isomorphism. So, inputs must also be equal. Since T is 1 to 1, we must have 0 equal to this. But these are what? These sigmas are coming from S, and we know that S already is a basis of V. So, in particular, S is linearly independent since the sigmas are all coming from S and S is linearly independent. All the scalars must be equal to 0. But see what we have now achieved. We started from here and we have now shown that all the scalars are 0. That means this sigma 1t, sigma 2t up to sigma mt, any linear combination of them will become 0 only when all the scalars are 0, and these sigma it's are arbitrary elements in ST. Hence, ST is linearly independent. So we have shown two things: ST spans W and ST is linearly independent, and hence by definition ST is a basis of W. And hence T maps the basis S onto S of V onto the basis ST of W. That completes the solution. Next, in this next one we have finite dimensionality. If V is finite dimensional and T is an isomorphism of V into V. Okay. T is an isomorphism of V into V, then T must be onto. Prove that T must map V onto V. So if you are dealing with homomorphisms from a vector space to itself, then and the vector space is finite dimensional, then one-to-oneness implies onto-ness, and vice versa. That we will see in the next exercise, but let us first see this one. So we now have an isomorphism from V into itself. That means a one-to-one homomorphism. We have to prove that T is onto. And in this regard, I want to say something else. In different algebra texts, this term isomorphism may have different meanings. For example, in Gallian's contemporary abstract algebra, isomorphism usually means, so far I have seen, a one-to-one onto homomorphism. That means it's a bijective homomorphism. Here, however, in Herstein's topics in algebra, an isomorphism is just a one-to-one homomorphism. It is not necessarily onto. Okay, so in that sense we are using isomorphism. Now we are given a finite dimensional vector space. So let n be defined to be the dimension of V, and because we have a finite dimensional space, let S be a basis of V. So that means S will have n number of vectors, n elements. since T is 1 to 1. T is 1 to 1, order of ST is equal to n. I'll explain what this thing is. Also, from the previous solution we see that ST is linearly independent. Okay, now what is happening here? We have a finite dimensional space having dimension n, fine, and let S be a basis of V. So S will have n number of vectors. Now next we say, since our homomorphism is an isomorphism, is 1 to 1, so ST also has, this set ST also has order, means the number of elements. That's how we denote cardinality or number of elements in this text. So order of ST is also n. If you are thinking why that is so, it is simple. No, say you have n number of elements in S, and you have a function T which is taking all these elements somewhere, and because this function T is 1 to 1, there is nothing like this. So there is no chance of the number of elements after the mapping has done its thing to be reduced. No chance of reduction. Whatever number of elements we have in S, an equal number of elements, equal number of images you will get by T. That is why the image of ST also has n elements, and the image of ST is ST, of course, because our function T maps V into V. This ST is again in V. It is some set in V which has n number of elements. Then we are saying also from the previous solution we see that ST is linearly independent. Now where is this coming from? If you go back to the previous solution, you will notice that linear independence of ST only depends on the fact that S is linearly independent. The fact that ST spans W, I am talking about the previous solution, depends on the fact that S spans V. So here we don't have anything to do with span. Okay, and anyway we don't have, I mean it's not given that T is onto, we are in fact going to prove that. So forget about span. We have a 1 to 1 function and we have the fact that S is linearly independent, and that is enough for us to prove that ST is also linearly independent, and in fact this is precisely what we did in the previous solution. Okay, so now our ST has n elements and it is linearly independent. Now when you have a linearly independent set in a vector space, we have already seen that you can put some extra necessary vectors if they become necessary in order to get a basis for the space, and the specific result is this. Have I written it here? Yes. So that is, you can blow up a linearly independent set into a basis for the whole space. We have already seen this result, and the name is lemma 4 to 5. Phi has a basis containing St. That is, you have V here, you have the set St here. We have proved that St is linearly independent. So you can put some extra vectors if the need arises to St, so that the resulting superset is a basis of V. Okay, so that means there is a basis which contains St. But now the fact that St has n elements will come into play. Because the dimension of the vector space itself is n and St already has n vectors, so actually there is no need to bring in some extra vectors from outside of St. Since order of St is equal to n, which is equal to the dimension of V, this implies St itself is a basis of V. Okay, but we are not done yet. We have done something, but we need to show that T is an onto map. So now using this, whatever we have achieved here, now we can show using that T is onto. So for that, let say, what shall we take? Phi. We can take P because we haven't taken anything here in this solution. Phi belong to Phi. Now because St is a basis of V, so this V is expressible as a linear combination of some basis vectors from St, then there exists S1, S2 to say S. We cannot take N because N is already taken here. So let us take M belonging to S and an equal number of scalars such that P is, remember what we are going to do. We are now using the fact that St is a basis of capital P. So Okay, so we have written V as a linear combination of some vectors from ST, but then V becomes this because T is a homomorphism. T, where this thing definitely belongs to our vector space. So we have realized this arbitrary vector small v as the T image of some vector again in V. Hence, T is onto, and that completes the solution. And its other version means the exercise complementary to this is exercise 6. If V is finite dimensional and T is a homomorphism, now it is given that T is onto, we need to prove that it is one-to-one. If V is finite dimensional and T is a homomorphism of V onto V, then we have to prove that T must be one-to-one and hence an isomorphism. Now here we will use a somewhat different route. Let W be C. T is a homomorphism from V onto V, so it will have some kernel. W be the kernel of T. Since T is a homomorphism of V onto V, so by the first isomorphism theorem, which is which one is which I forgot. No, I remember, this is theorem 411 by theorem 411 because it comes in the first section. V is isomorphic to V by W. recall that if you there you had this now T is a homomorphism from say V to, actually we had W I think, or we had this specifically. T is a homomorphism from U into V, and say W is the kernel of this homomorphism, then U by W is isomorphic to V. And we in fact need ontoness here, so that the image is this entire V. Even if you don't have onto function, the quotient U by W will still be isomorphic to something, but that something will then not be the entire V, it will be a subspace of V, okay, a proper subspace of V. Now here what we have, in place of U we have V, in place of V of course we have V, and our W is W, so V by W is isomorphic to V, okay. And this result does not assume anything about finite dimensionality or like that, it's just simply true in general. But now we impose the fact that V is finite dimensional. Since V is finite dimensional, we have by lemma 4 to 6. Now in this lemma, it's recall, this is the lemma where we learn how to calculate the dimension of the quotient space. It equals the dimension of V minus dimension of W, it's that thing. First of all, we use this, the fact that these two are isomorphic. So because V is finite dimensional, this quotient space will also be naturally finite dimensional, and because of this isomorphism, their dimensions, they have the same dimension. So we get this dimension of V is equal to the dimension of V by W, but here then we use lemma 4 to 6 and write this equal to dimension of V minus dimension of W. Now what do we have from this equation? Dimension of V equal to dimension of V minus dimension of W, namely that this dimension should be equal to 0. This implies now there is only one vector space whose dimension is 0, namely the 0 space. Any vector space which has more than one element will have non-zero dimension, will have a positive integer integral dimension, and hence W is the 0 space. But W is the kernel of T, so that means the kernel of T is the trivial subspace. This proves that T is 1-to-1 and hence an isomorphism. So that's what we wanted to show. And this one is also over. Let us solve two more. 7, if V is of dimension n, show that any set of n linearly independent vectors in any set of n linearly independent vectors in V forms the basis of V. Let S be a set of n vectors in P. If you either don't write this or don't mention that S is a subset of V, then of course that will not be correct, because just simply taking a set of n elements does not tell us that necessarily they are coming from the vector space V. So this tells us that these vectors are in V. B a linearly independent set of n vectors. Okay. Now we need to prove that S is actually a basis for V. So already it's linearly independent. We now have to show that it spans V. Clearly, Vi belongs to the linear span of S for all I lying between 1 and n. In a trivial manner, each Vi is a linear combination of these Vj's, where in particular it is that linear combination where only the coefficient of Vi is 1 and the other coefficients are 0. Okay, so in particular these are also vectors in V. No, so they are linear combinations of elements in S. Now we look at the other vectors. So let W belong to V minus L of S. If it happens that the linear span, oh no, that's not what I wanted to write. If it happens that this S itself is all of V, then fine, and you have just simply the fact that S spans V, because S is in fact all of V in a trivial manner. But if you have something outside, so we have taken one such thing from outside, then W, V1, V2 Pn is a set. Okay, let's just write it as a set. This is a set of n plus 1 vectors in V. Now it is given that V has dimension n. So any linearly independent set must have size less than or equal to n. If you have a set whose size exceeds n, it cannot be linearly independent. It has to be linearly dependent. And this fact is coming from your lemma 424 by lemma 424. This set is linearly dependent over F. Those things are there in the background. Okay. Hence, but if it is linearly dependent, then some non-trivial linear combination of these vectors will give us the zero vector. Then there exists scalars not all zero such that this linear combination is equal to 0. All the alpha i's cannot be 0. Also, all the alphas, including this one also, cannot be simultaneously 0. At least one alpha should be non-zero. Now, if this scalar itself becomes 0, then this term will vanish and we will have this but using the linear independence of these VI's, we would then have all the alpha i's also equal to 0, because you see this we have in fact taken S to be linearly independent. So if alpha is 0, the first term vanishes and we are having the rest, and oh, I forgot to write this equal to 0. Okay, it's an equation, not just an expression. Then we have this, and because these VI's are linearly independent, we would then have all the alpha is also 0, but then all the scalars are 0, which is not true. according to our hypothesis, all of them are not simultaneously 0, a contradiction. Hence, we must have alpha not equal to 0. Thus, now if alpha is non-zero, then we can express W itself as a linear combination of the Vi's in this way. Minus alpha inverse alpha 1 V1 minus alpha inverse alpha 2 V2. You can see, you can understand what we have done here. And alpha inverse exists because it's a non-zero field element now. Thus, we have Ls equal to V. Hence, S is a basis of V. That's what we wanted to show. In an n-dimensional vector space, any n number of linearly independent vectors, automatically they give us a basis. And there is one more, quite an easy one. With that, let's just finish things for tonight. If V is finite dimensional and W is a subspace of V, V is finite dimensional and W is a subspace of V such that they have the same dimension, then V must be equal to W, or W must be equal to the same thing. So even if you have an infinite vector space where there are infinitely many vectors, you cannot have a proper subspace of that vector space having the same dimension as the vector space. Of course, we are talking about finite dimensional spaces. It must be equal to the vector space itself. So if you find a proper subset, a proper subspace of a finite dimensional vector space, then its dimension is strictly less than the dimension of the vector space, which however cannot be concluded simply from this result. It also needs that thing which says that in general the dimension of a subspace is less than or equal to the dimension of the original space. Okay, so let us now see the solution. We have to use that result itself, which is lemma 426. Have we gone directly or okay by lemma 4 to 6. What happens to this quotient space? Its dimension is dimension of V minus dimension of W. That now becomes 0. This thing becomes 0. Now the quotient space has dimension 0, that means it's the 0 space. Hence, the quotient space is the 0 space. What will you write here in terms of W? Recall that the elements in this quotient space, the vectors in this quotient space are cosets of W in V. So the fact that it's the 0 space and hence the dimension is 0 tells us that it consists of only the 0 element, which is W. Okay. So this is equal to W. So that means what? If you have anything in V outside of W, will that thing give you this coset itself? Of course not. If you have something in V which is not in W, then this coset of W will be distinct from this 0 coset. So that means we cannot have anything in V outside of W. That is, V is all of W. There is nothing outside of W in V. But we of course won't write these elementary things in the solution. We just simply write, so we must have V equal to W, and this completes the solution. There are others also after this, of course, and we will solve these things in the next vector space update. Today is Friday, so tomorrow again we will go back to Gallian's exercises and solve some of them, both from groups and rings. So there will be 2 videos tomorrow, and then we will have analysis on Sunday. So that will be all for tonight. If you want to say something about these things, you can write in the comment section below, or you can mail me at my usual email ID, which the link will be there in the description. So with that, I sign off. See you tomorrow with Gallian's exercises. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.